So now we want to talk about one of the most common types of systems that you design. That's high-performance measurement systems. For over 25 years, you've been using LabVIEW and our data acquisition hardware to design these sophisticated measurement systems. This is an area we continue to invest in, and we've got some very exciting new products to show you here this morning. So to help me do that, I want to bring out two of the leaders from our R&D group and data acquisition R&D group, Director of R&D, Stephanie Breyer, and Group Manager, Tom Walling. Welcome up. Hey, Stephanie.
Morning, Eric. Thank you.
Good morning. Morning, Tom.
So as most of you know, CompactDAQ is a modular data acquisition platform for USB, Ethernet, and Wi-Fi that provides sensor and electrical measurements. CompactDAQ is one of NI's most successful platforms with over 1.5 million channels sold. Our R&D teams have been continuing to develop new products, and today we are announcing new additions to the platform, including a 4-slot Ethernet chassis and a new C-Series module that allows you to synchronize clocks between chassis. Now, based on this extensive ecosystem, you, our customers, have developed a variety of applications ranging from the crash testing of safety helmets to monitoring the construction methods of mobile health clinics in Africa. One major point of feedback that we've received from you over the years is the ability to use CompactDAQ in a more standalone fashion without the need for the use of a tethered PC for applications like embedded monitoring and data logging. So based on that feedback, today I'm very excited to announce a new line of standalone CompactDAQ products.
So I see, with the new standalone DAQ, you can run an application completely embedded on the chassis without the need for tethered PC.
Yes, Eric, that's true. So for the first time, CompactDAQ includes an Intel Core i7 dual-core processor, 32 gigabytes of onboard non-volatile storage, a variety of high-performance peripheral I/O ports, and runs your choice of embedded OS, either Windows Embedded or, for extreme reliability, LabVIEW Real-Time. Like all of our CompactDAQ chassis, standalone CompactDAQ supports over 50 C-Series I/O modules for analog, digital, and CAN inputs and outputs that allow you to add and replace modules as your I/O needs change. The software experience with LabVIEW and DAQ MX is perfect for high-performance streaming applications with embedded timing and synchronization.
Okay, so you mentioned embedded monitoring. Why don't we talk a little bit about some applications that need that capability?
Sure, so one application area that could really benefit from standalone CompactDAQ is in-vehicle data logging. As vehicles become more complex, in-vehicle data logging systems must support a breadth of I/O along with high-performance processing and logging capabilities to allow you to acquire, analyze, and log large amounts of data. So using standalone CompactDAQ, we have created a high-performance, flexible, in-vehicle data logging system for our smart car here that will allow us to perform dynamic chassis testing, engine testing, and driver response testing, all with one integrated system.
So I see there's all kinds of sensors and wires throughout this car, so tell everyone about some of the things you're monitoring on the smart car.
Sure, so for dynamic chassis testing, we've instrumented the smart car with accelerometers to track lateral acceleration, and with strain gauges to determine the deflection of the frame as we drive. So a structural engineer may want to use this data to help determine if the car is likely to roll or how the frame of the car responds as you navigate a sharp turn in order to help improve automobile safety. So we can't really drive the car this morning, but we would like to show you some real data. So Eric, could you help simulate that by pushing on the car for us?
Yeah, let me limber up. You sure I'm not going to break it?
Please be careful.
Okay, yeah, I see.
So on the LabVIEW front panel, you can see data from the sensors. As we switch over to the LabVIEW block diagram, we are acquiring data using DAQ MX, which is the same driver software that we use across the entire CompactDAQ product line.
So just so everyone knows, you're actually running LabVIEW, the development environment down here, and that's what Tom's showing. And so it's pretty much ready for deployment.
That's correct. So you can develop on the standalone CompactDAQ chassis, and then when you want to run it headless or embedded, all we would need to do really is remove the VGA cable. We're ready to take the car out to the track and log data. Now, we do realize that a lot of engineers still want to be able to view their data as it's being acquired. So Tom, could you show us how to accomplish that?
Sure. So let's say I want to display live data on this iPad here. I can use the same LabVIEW application to publish LabVIEW shared variables through a wireless connection from the standalone CompactDAQ system. I'll just add a couple of variables, restart the application, and now the iPad can connect and display the measurements in Data Dashboard for LabVIEW.
There you go. Cool. That's awesome. I just like the fact that I can just shake the car like that. Okay, you mentioned engine testing, driver response testing. How about those?
Right, so for those types of applications, we did need to log data as we were driving. So Tom and I took the car out to a local track. While we were there, we started talking about Formula One coming to Austin, and well, here's what happened next.
Who knew a smart car could be that much fun?
Yes, so we did have some fun, but it wasn't all fun and games. While we were out there racing, we were able to acquire data from the car, such as engine position, cylinder pressure, throttle position, and pedal position. We also acquired location data as well as video of the road using external devices that were connected to the peripheral ports.
Right, and because we had an integrated high-performance processor, we're able to analyze that data, but also log it to disk using LabVIEW and NI-DAQ-MX. So once we get back into the lab, we can use DIADM to view and play back the data to see how the racing went. Here's a view of some of that data, some video, position, and some of the engine parameters. For example, in the lower right corner, you can see a PV diagram. It's a graph of pressure versus volume for one of the cylinders in the engine. And the area inside that curve represents the amount of work being performed by the engine. So maximizing that area actually allows us to extract as much energy as possible from each drop of fuel.
Okay, so you're testing the chassis. That's engine testing with the PV diagram. You also mentioned driver response testing.
Right, so we were racing. So you would kind of expect to be keeping the pedal to the metal and trying to keep your speed high throughout. So we can look at some of the data side by side from different runs. And you can see that one of the drivers, we won't say who, tended to kind of hold back a little bit more in some of the curves, whereas the other driver was able to kind of keep that pedal pressed to the floor pretty much the whole time.
I'm pretty sure only one of you was racing, Tom.
So actually, I think Tom may have just gotten those labels switched on the graphs. So, but seriously, we've been able to show you how we performed chassis testing, engine testing, and driver response testing, all with one standalone CompactDAQ system. Using NI's modular hardware approach, you can mix and match the over 50 C-Series I/O modules to create a wide variety of measurement I/O systems. Combined with LabVIEW, standalone CompactDAQ is one of the world's most flexible, highest performance embedded measurement systems to meet your needs today and adapt to tomorrow's changing requirements.
Very cool. Thank you, Stephanie and Tom, for a great new product and having a little fun, too. Thank you.